How many spanning trees does a complete graph with n vertices have? This might sound like a simple problem, but there is no straightforward method to solve it. In this video, we will explore proof that involves double counting, but instead of counting the number of spanning trees, we will calculate the number of parts. Here you might ask that what is part? Part stands for plans of ensemble of a rooted tree. It's basically a rooted tree where every edge has a label from 1 to n. Here is an example of part. First, counting. The simplest way to count the number of parts is with the number of spanning trees. We can pick n different roots as there are n vertices, and there are n-1 factorial ways to label the edges for every tree. Therefore, the number of parts is n times n-1 factorial times kappa kn, where kappa kn is the number of spanning trees of complete graph with n vertices. The other way is more complicated compared to the first one. We first interpret a rooted tree as a directed graph where all edges are oriented towards the root. As there is no edge away from the root, the out-degree of root will be 0, and other vertices will have an out-degree of 1. We start with an empty graph of size n and keep adding edges one by one until we are left with a tree. As an edge can be defined by its tail and head, the number of possible directed edges at every step is a product of the number of ways to choose the head and the tail. For the first step, we have a forest of n empty rooted trees. Since we have n ways to choose the head and n- ways to choose the tail, there are totally n times n-1 possible options for the first arrow. In the second step, the arrow has to be different from the first and has to satisfy an extra condition. Since all edges point towards the root, every vertex has an out-degree at most 1, hence the tail of the second arrow has to be different from the tail of the first one. Thus we have n times n-2 possibilities for the second arrow. Generally, when we choose a case edge, we can pick any of n vertices as a head, but when it comes to the tail, we have a few restrictions. First, a new edge cannot create a cycle, though we can easily avoid this by simply ignoring the vertices within the same component as the head. But most importantly, the out-degree of the tail must be 0. Otherwise, the out-degree after addition will exceed 1. As only the root of the component can have an out-degree of 0, and there are n-k components, we only have n-k-1 options for the tail. Consequently, there are n times n-k-1 ways to pick the case edge. After repeating this process n-2 times for every edge, we obtain the following formula and simplify it. And in the end, we solve for the kappa kn. This theorem is called Cayley's theorem after British mathematician Arthur Cayley. A century later, Jim Pittman, a statistician from University of California at Berkeley, found this proof. Compared to other proofs for this theorem, this proof is considerably shorter and easier.